friends, as a part of his research studies, conducted a survey to check the reliability of COVID test. Of people having COVID, 85% of the tests detect the disease, but 50% go undetected. As per the earlier clinical reports that he found, of people free of COVID, 98% are just COVID negative, but 2% are diagnosed as COVID positive. From a large population of which only 0.1% have COVID, one person is selected at random, given the COVID test, and the pathologist reports him as COVID positive. Then, what is the probability that the person actually has COVID? Can you solve this question using probability theorems? Yes, of course. The theory behind such real-life situations is Bayes' theorem. It's named after the famous mathematician John Bayes. And before going in detail, we should also know how a sample space is partitioned. Partition of a sample space. It is a collection of disjoint events E1, E2, E3 up to En, whose union is the sample space. That is, Ei intersection Ej equals null set, where I not equal to j. E1 union E2 union up to En will be equal to what? The sample space. Also remember, for the same sample space, there can be many different partitions. That means partition of a sample space is not unique. Next, we will develop an idea about total probability. Now, when the probability of occurrence of any of these events in the sample space is dependent on the occurrence of other events, then total probability is to be used to find the probability of that event. The theorem of total probability states that if E1, E2, En represents a partition of a sample space such that the probability of occurrence of any of these events are non-zero, then the probability of an event A associated with the sample space is given by P of A is equal to P of E1 into P of A given E1 plus P of E2 into P of A given E2, so on up to P of En into P of A given En. And as summing up, we get P of A is equal to summation j equal to 1 to n P of Ej into P of A given Ej, where P of A given Ej is a conditional probability. Now, let's see the theorem proof. Given that E1, E2 up to En is a partition of the sample space, yes. Therefore, we can write S is equal to E1 union E2 union up to En. Again, Ei intersection Ej is equal to phi, where I is not equal to j. Now, for any event A, we can write A is equal to A intersection S. Again, what is S? A intersection E1 union E2 union up to En. And now, this can be written as A intersection E1 union A intersection E2 union up to A intersection En. It is clear that A intersection Ei and A intersection Ej are the subsets of Ei and Ej. Therefore, A intersection Ei and A intersection Ej are also disjoint, since Ei and Ej are disjoint. So, the probability of event A is calculated as, so P of A is equal to P of A intersection E1 union A intersection E2 union up to A intersection En. Taking P inside, we get P of A intersection E1 plus P of A intersection E2 and so on up to P of A intersection En. Again, this can be written as P of A intersection Ei is equal to P of Ei into P of A given Ej, where P of Ei not equal to 0 by the multiplication rule of probability. Therefore, P of A is equal to, substituting this in this equation, we get P of E1 into P of A given E1 plus P of E2 into P of A given E2 and so on. The nth term will be P of En into P of A given En. And again, we can rearrange it and we get the final equation P of A is equal to summation j equal to 1 to n P of Ej into P of A given Ej. Thus, we have proved the probability of occurrence of an event A is dependent on the occurrence of other events in the sample space. Alright. Next, we will aim at understanding the Bayes theorem, its statement, formula and derivation with the help of examples. Bayes theorem is also known as Bayes rule. It is a mathematical formula based on the concepts of conditional probability of events. It is a method used to determine the probability of events based on the occurrence of prior events. The concept behind Bayes theorem is nothing but reverse probability. Let's take the theorem and derivation. P of EI given A is equal to P of EI into P of A given EI, the whole divided by summation j equal to 1 to n P of Ej into P of A given Ej for any I ranging from 1 to n, where what is this P of EI given A? P of EI given A is the probability of the event EI occurring given the event A has occurred. So, conditional probability. Now, what is P of A given EI? It is the probability of event A occurring given that EI has already occurred. Now, what is PI? P of EI is the probability of each event. Okay, now let's see the proof. P of EI given A is equal to P of A intersection EI, the whole divided by P of A. It is a conditional probability theorem. Now, by the multiplication rule of probability, we can write this equation as P of EI given A is equal to P of EI into P of A given EI, the whole divided by P of A. Now, by the theorem of total probability, P of A can be again written as P of EI given A is equal to P of EI into P of A given EI, the whole divided by expanding PA, that is summation j equal to 1 to n P of Ej into P of A given Ej. This is a theorem. Hence, we have proved it. Now, suppose we have estimated the prior probabilities for the events we are concerned with and then obtain a new information. Our aim is to find the posterior probability. Here, Bayes theorem gives us a way to do this. Bayes theorem helps in relating the posterior probability with the prior probability, where P of EI is the prior probability and the conditional probability P of EI given A is called the a posteriori probability of the hypothesis EI. So, as per the equation, E1, E2, En are called hypotheses, right? Now, coming back to the example with which we started our discussion of people having COVID, 85% of the tests detect the disease, but 15% go undetected. As per the earlier clinical reports that we found of people free of COVID, 98% are checked COVID negative, but 2% are diagnosed as COVID positive. Now, from a large population of which only 0.1% have COVID, 1% is selected random, given the COVID test and the pathologist reports him as COVID positive. Then what is the probability that the person actually has COVID? This was the question we started with. Now, can you find the solution for this? Yes, we can use a Bayes theorem to find it, right? Let E represents the event that the person selected has COVID. Now, let F represents the event that the person selected does not have COVID. Now, we need one more parameter, that is G, which represents the event that the test judges COVID positive. Now, our aim is to find the probability that the person selected actually has COVID if the test judges COVID positive correctly. That is, we need to find P of E given G. This can be written as P of E given G is equal to P of E into P of G given E, the whole divided by P of E into P of G given E plus P of F into P of G given F. So, we will find each parameter in this equation. So, what is P of E? P of E is the probability that the person selected has COVID, which is nothing but 0.1%, that is equal to 0.001. Now, what is P of F? P of F is probability that the person selected does not have COVID. So, which can be found by 1 minus P of E. So, the answer will be 1 minus 0.001, which is equal to 0.999. Now, what is P of G given E? It is the probability that the test judges COVID positive if the person actually has COVID. That is nothing but 85%. So, which will be 0.85, which is the true positive value. Now, P of G given F. It is represents the probability that test judges COVID positive if the person does not have COVID. That is 2%. And we get it as 0.02, which is actually what? It gives the false negative rate. Now, substitute all these values in the equation base theorem. We get P of E given G is equal to 0.001 into 0.85, the whole divided by 0.001 into 0.85 plus 0.999 into 0.02. Now, rearranging, we get 85 into 10 raised to minus 5 divided by 10 raised to minus 5 into 85 plus 1998. On solving, we get the final answer as 0.0408. So, the probability that a person selected random is actually having COVID, given that he is tested COVID positive, is 0.0408. Thus, the use of Bayes' theorem can be employed in many fields than statistics, with medicine and pharmacology serving as two prominent examples. The theorem is very frequently used in various branches of finance in predicting the likelihood that an investment will succeed. Just a few examples. Now, it's time to wind up this entire section. Let's have a look at the summary.
Manorama Horizon. Learning made simple.